1999, a team of physicists at the University of Maryland, Baltimore County, fired a laser into a crystal and broke the way we think about time. That is the version you have probably heard. And it is wrong. But the truth, the actual result of what happened in that lab, might be harder to accept than time travel. Here is what they did. They took a single photon, split it into two entangled twins, and sent those twins down different paths. One twin hit a detector immediately. The other twin traveled a longer route, about 2.5 meters longer, which means it arrived roughly 8 billionths of a second later. And during that extra journey, the second twin encountered a choice. A beam splitter would either preserve information about which path the first twin had taken, or erase that information entirely. The decision happened after the first twin was already detected and recorded, already done, already in the past. And yet, when the physicists sorted through their data, the first twin's behavior appeared to change depending on what happened to the second twin later. Photons, whose partners had their path information erased, showed interference, the signature of a wave. Photons, whose partners kept their path information, showed no interference, the signature of a particle. The first twin seemed to know, before it was recorded, what would happen to its partner in the future. If that sounds like the future is reaching back to rewrite the past, you are not alone. Hundreds of YouTube videos, popular science books, and even some physicists have made exactly that claim. But they are wrong, and the reason they are wrong reveals something about reality that is, if you sit with it long enough, far stranger than backwards time travel. To understand what actually happened in that Baltimore County lab and why it matters, we need to go back about 220 years to a physician in London who picked a fight with Isaac Newton's ghost and lost, and then turned out to be right. Thomas Young was not supposed to revolutionize physics. He was a doctor, a practicing physician in London at the turn of the 19th century, with a patient list and a medical degree, and absolutely no business overturning a century of settled science. But Young had a problem that a lot of brilliant people have, which is that he could not stop being interested in things. By the age of 14, he had taught himself Greek, Latin, French, Italian, Hebrew, Arabic, Persian, Turkish, Syriac, and an Ethiopian language called Ge'ez. He would later make critical contributions to deciphering the Rosetta Stone. He studied the human eye and proposed the first theory of color vision. He calculated the elastic properties of materials so precisely that the fundamental measure of stiffness is still called Young's modulus. The man could not encounter a problem without trying to solve it. And in 1801, the problem that caught his attention was light. At that time, Isaac Newton's theory of light was not merely dominant, it was essentially sacred. Newton's optics, published in 1704, described light as a stream of tiny particles, what he called corpuscles, traveling in straight lines. Christian Huygens had proposed a competing wave theory back in the 1690s, but Newton's reputation was so immense that Huygens' idea had been effectively buried for 100 years. Questioning Newton on light in 1801, England was roughly equivalent to questioning Einstein on relativity in 1960. You could do it, but you had better be right, and you had better have proof. Young had proof. His experiment was deceptively simple. He took sunlight, passed it through a tiny pinhole to create a coherent source, then aimed that coherent beam at a barrier with two narrow slits cut into it. Behind the barrier, he placed a screen, and on that screen, he saw something that Newton's particle theory could not explain. Alternating bands of light and dark, bright stripes where the waves from the two slits arrived in sync and reinforced each other. Dark stripes where they arrived out of sync and cancelled each other out. This is interference. It is what happens when you drop two pebbles into a pond and watch the ripple patterns overlap. Peaks meeting peaks make bigger peaks. Peaks meeting troughs make flat water. Young was watching light behave exactly like water waves. He presented his findings in his 1803 Beckerian lecture to the Royal Society, writing that two equal series of waves proceeding from centers near each other may be seen to destroy each other's effects at certain points, and at other points to redouble them. He even estimated the wavelengths of different colors. His value for yellow light, converted to modern units, was 576 nanometers. The accepted value today is 577. He was off by a single nanometer 2 centuries before anyone had the instruments to measure at that scale. The scientific establishment destroyed him for it. Henry Brougham, writing anonymously in the Edinburgh Review, published 3 separate attacks between 1803 and 1804. He called Young's work destitute of every species of merit. He mocked the fertile yet fruitless brain of the eternal Dr. Young. A publisher who had agreed to print Young's lectures backed out under the pressure. Young essentially gave up on optics entirely, retreating into medicine and Egyptology. It would take Augustin Jean Fresnel's independent mathematical treatment of wave theory around 1816 and James Clerk Maxwell's electromagnetic theory in the 1860s to fully vindicate what Young had shown in that sunlit London laboratory. Young considered establishing the wave theory of light his most important achievement. He was right, but neither he nor anyone alive in 1803 could have imagined what would happen when his simple experiment was repeated a century later with a crucial modification. What if you sent the light through one photon at a time? Think about what Young's experiment means if light is made of particles. If you fire a machine gun at a wall with 2 holes in it, you get 2 clusters of bullet holes on the wall behind. You do not get an interference pattern. Bullets are particles. They go through one hole or the other. They do not interfere with each other. So if light is made of particles, photons, and you send them through 2 slits, you should get 2 bright patches on the screen behind. No interference, no alternating bands, just 2 blobs. But that is not what happens. In 1909, Geoffrey Ingram Taylor at Cambridge set out to test this. He attenuated a light source to what he described as the equivalent of a candle burning at a distance slightly exceeding a mile. At that intensity, fewer than 1 photon existed inside the apparatus at any given moment. There was no crowd of photons that could interfere with each other. Each photon was alone. Taylor exposed photographic plates for up to 3 months to accumulate enough data. The interference pattern was identical to what you get with full-intensity light. This inspired Paul Dirac's famous statement in The Principles of Quantum Mechanics. Each photon then interferes only with itself. Think about that for a second. A single photon, a single particle of light, passes through 2 slits and somehow interferes with itself on the other side. as if it went through both slits simultaneously, as if a single bullet fired at a wall with two holes somehow passed through both holes at the same time and hit itself on the other side. But the most stunning visual demonstration came 80 years later, in 1989, at the Hitachi Advanced Research Laboratory in Japan. Akira Tonomura and his colleagues used a device called an electron biprism, which is functionally equivalent to a double slit, to send individual electrons through the apparatus one at a time. These were 50,000 electron-volt electrons moving at a significant fraction of the speed of light, with a flight time through the apparatus of about 11 nanoseconds each. At roughly 3,000 electrons per second, the probability of two electrons being inside the device simultaneously was essentially zero. They recorded the results at different stages, and the images are among the most beautiful in all of physics. After 10 electrons, you see 10 random dots. No pattern whatsoever, just noise. After 200 electrons, still mostly noise. Maybe a faint hint of something if you squint. After 6,000, you can start to see it. Faint stripes emerging from the chaos. After 40,000, the pattern is unmistakable. Alternating bands of high and low electron density, interference fringes. After 140,000 electrons, the pattern is textbook perfect. Every single electron arrived as a dot, a particle hitting a specific point on the detector. But collectively, over thousands of individual particle impacts, they traced out a wave interference pattern. In 2002, readers of Physics World voted this the most beautiful experiment in physics. It earned that title. But here is the thing that should keep you up at night. Each electron went through the apparatus alone. There was nothing to interfere with. And yet, it interfered. The wave pattern is not a property of the collection of electrons. You cannot explain it by saying the electrons bumped into each other or communicated somehow. Each one, individually, carried within it the probability of landing at every point on the detector, and those probabilities were distributed in a wave-like pattern that only became visible when enough electrons had landed to reveal the underlying statistics. Richard Feynman, who understood this better than almost anyone, put it bluntly in his 1965 Lectures on Physics. They do not behave like waves. They do not behave like particles. They do not behave like clouds or billiard balls or weights on springs or like anything that you have ever seen. Feynman also said that nobody understands quantum mechanics, and he meant it. Not that nobody can do the math. The math works perfectly, but nobody has a satisfying picture of what is actually happening between the moment a photon leaves its source and the moment it hits a detector. The math tells you the probabilities with extraordinary precision. It refuses to tell you the story. But the double-slit experiment was about to get much stranger, because physicists, being physicists, could not resist asking the obvious next question. If a single photon goes through both slits at once, what happens if you watch it? Here is where the popular version of the story goes off the rails, and where we need to be very precise about what actually happens. The standard telling goes like this. If you put a detector at the slits to see which one the photon goes through, the interference pattern vanishes. The photon behaves like a particle, going through one slit or the other, and you get two blobs instead of fringes. Remove the detector, and the interference returns. The photon goes back to behaving like a wave. The conclusion, as stated in countless pop science videos, is that observation collapses the wave function. The act of looking changes the outcome, and people hear observation and think consciousness. They think the human mind is somehow reaching into the quantum realm and forcing particles to make up their minds. This is wrong. Consciousness has nothing to do with it. But the old explanation for why detection kills interference is also incomplete, and getting this right is essential to understanding the quantum eraser. The traditional explanation invoked Heisenberg's uncertainty principle. The detector, by interacting with the photon to determine its position at the slit, necessarily gives it a random kick of momentum. This momentum disturbance randomizes the photon's trajectory just enough to smear out the interference pattern. Detection disturbs the system, and the disturbance destroys the delicate phase relationships needed for interference. This explanation is intuitive. It makes mechanical sense. And in 1991, Marlon Scully, Berthold Georg Englert, and Herbert Walter published a paper in Nature that demolished it. What Scully and his colleagues showed was that you can obtain which path information. You can determine which slit the photon went through without giving the photon any significant momentum kick at all. Their proposal used atom interferometers with tiny microwave cavities. An atom passing through one slit would leave a photon in one cavity. An atom passing through the other slit would leave a photon in the other cavity. The which path information was stored not in the atom's disturbed momentum, but in the state of the cavities. The atom itself was barely touched, and the interference pattern still vanished. This was confirmed experimentally in 1998 by Stefan Dürr, Thomas Nonn, and Gerhard Rempe at the Max Planck Institute for Quantum Optics. In their atom interferometer, the momentum disturbance from path detection was measured and found to be far too small to explain the disappearance of interference. Something else was going on. That something else was entanglement. When the which path detector interacts with the photon, even gently, even without any mechanical disturbance, it creates a quantum correlation between the photon and the detector. The photon's state becomes entangled with the detector's state. Mathematically, the combined system enters a state where the photon going through slit 1 is paired with the detector reading slit 1, and the photon going through slit 2 is paired with the detector reading slit 2. These two components of the overall quantum state can no longer interfere with each other because they are now distinguishable. They are tagged. The phase relationship between the two paths, which is the entire source of the interference pattern, has been transferred from the photon alone to the larger entangled system. This process is called decoherence, and it does not require consciousness, intelligence, or even a functioning detector in any human sense. It requires only that some physical system, anything at all, becomes correlated with the which path information. Air molecules bumping into the photon near one slit would do it. A stray thermal photon scattering off the particle would do it. Any interaction that creates even the possibility, in principle, of determining which path was taken will suppress interference, whether or not any human ever actually checks. The quantitative version of this was formalized in 1996 as the Englert Greenberger duality relation. It states that d squared plus v squared is less than or equal to 1, where d is distinguishability, a measure of how much which path information is available, and v is visibility, a measure of how clear the interference fringes are. Perfect which path knowledge means d equals 1, which forces v to equal 0. No interference. Perfect interference means v equals 1, which forces d to equal 0. No path information. You can have partial amounts of both, but the total is constrained. The universe enforces a strict budget between knowing and interfering, and it never allows you to exceed it. This is Bohr's complementarity principle, formulated at the Como Conference in September of 1927, but expressed with mathematical teeth. Wave behavior and particle behavior are not just different descriptions. They are complementary aspects of a single quantum reality that cannot both be fully manifest in the same experimental arrangement. But to understand how we arrived at this strange place, how physics went from Newton's clean certainty to a principle that tells you the universe has a budget for knowledge, you need to understand the argument that shaped the entire 20th century of physics. It is the argument between two of the greatest minds in human history, and it lasted from 1927 until one of them died, and in a sense, it is still going on. Albert Einstein hated quantum mechanics. That is not quite right. He helped create it. His 1905 paper on the photoelectric effect, the one that won him the Nobel Prize, was the paper that introduced the idea of light quanta, what we now call photons. Without Einstein, there might be no quantum mechanics at all. What Einstein hated was not the mathematics. He accepted that the equations worked. What he hated was the interpretation. The claim, advanced most forcefully by Niels Bohr, that quantum mechanics was complete, that there was nothing more to be said about physical reality beyond what the wave function and its probabilistic predictions provided. Einstein believed there had to be something underneath, some deeper layer of reality where particles had definite properties at all times, where causes preceded effects, where God, as he famously put it, did not play dice. He spent the last 3 decades of his life trying to prove that quantum mechanics was incomplete, that it was a useful but ultimately superficial description of a deeper, more rational reality. Their public battle began at the 5th Solvay Conference in Brussels in October of 1927. It was one of the most extraordinary gatherings in the history of science. The photograph from that conference, 29 men and 1 woman standing on the steps of the Hotel Metropole, includes 17 Nobel laureates: Einstein, Bohr, Heisenberg, Schrödinger, Dirac, Planck, Curie, Born, Lorentz, de Broglie. The concentration of genius per square meter has probably never been exceeded. The debates did not happen in the formal sessions. They happened at breakfast. Einstein would arrive at the dining room in the morning, sit down with his coffee, and present a thought experiment designed to break quantum mechanics. A physical scenario where, he argued, you could simultaneously know both the position and momentum of a particle. Violating Heisenberg's uncertainty principle, Bohr would listen, turn pale, and spend the rest of the day working through the argument with Heisenberg and Pauli. By dinner, he would have found the flaw. Paul Ehrenfest, who attended both conferences, described the spectacle in a letter. It was delightful for me to be present during the conversation between Bohr and Einstein, he wrote. Like a game of chess, Einstein all the time with new examples, a kind of perpetual motion machine of the second kind to break the uncertainty relation. Bohr from out of a cloud of philosophical smoke, constantly searching for the tools to crush one example after another. The pattern repeated at the 6th Solvay Conference in 1930. Einstein unveiled his most ingenious challenge yet. He proposed a box containing a single photon with a clock-controlled shutter that would open for a precisely known interval, releasing the photon at a precisely known time. By weighing the box before and after using Einstein's own mass-energy equivalence, E equals mc squared, you could determine the photon's energy with arbitrary precision. Combined with the precise timing of the shutter, this would give you both the energy and the time of emission simultaneously, violating the energy-time uncertainty relation. Bohr was reportedly shaken. He spent a sleepless night working through the problem. And by morning, he had found a devastating response. Bohr showed that weighing the box required it to move in a gravitational field, and by Einstein's own general theory of relativity, clocks run at different rates at different gravitational potentials. The very act of measuring the energy through the box's weight introduced an uncertainty in the timing of the shutter. When you worked through the math, Einstein's own theory of gravity enforced Heisenberg's uncertainty principle. Einstein had been defeated by his own creation. Einstein never accepted this outcome, but he shifted his strategy. Rather than trying to break the uncertainty principle directly, he turned to a more fundamental argument. Rather than showing that quantum mechanics made wrong predictions, he would show that it made incomplete predictions, that there were elements of physical reality that quantum mechanics simply failed to account for. This led to the most famous paper in the history of quantum foundations. Published in Physical Review on May 15, 1935, authored by Einstein, Boris Podolsky, and Nathan Rosen, it bore the title, "Can Quantum Mechanical Description of Physical Reality be Considered Complete?" It is known universally as the EPR paper. The argument is elegant and, within its assumptions, airtight. Here is how it works. Consider two particles that interact and then fly apart. Quantum mechanics predicts that certain properties of these particles are correlated. If you measure the position of particle 1, you can predict with certainty the position of particle 2 without ever touching it. If instead you measure the momentum of particle 1, you can predict with certainty the momentum of particle 2. Your choice of what to measure on particle 1 determines what you can predict about particle 2, even though the particles may be separated by any distance. EPR made what seemed like a reasonable assumption, which they called the criterion of reality. If, without in any way disturbing a system, we can predict with certainty the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. In plain English, if you can predict a measurement result with absolute certainty without touching the object, then the property must have been real and definite before you measured it. Combined with locality, the assumption that measuring particle 1 cannot instantaneously affect particle 2 far away, the conclusion seemed inescapable. Since you can predict either the position or the momentum of particle 2 by choosing what to measure on particle 1, and since your measurement on particle 1 cannot physically affect particle 2. Both properties must have been definite all along. The position and momentum of particle 2 were both real, definite, existing simultaneously. But quantum mechanics says you cannot know both simultaneously. The uncertainty principle forbids it. Therefore, EPR concluded, quantum mechanics is incomplete. There must be additional variables hidden from the quantum formalism that specify the definite properties particles have before measurement. Einstein called the alternative spooky action at a distance. If quantum mechanics was complete and particles did not have definite properties until measured, then measuring particle 1 must somehow instantaneously influence particle 2, no matter how far apart they were. Einstein considered this absurd. It violated the spirit of relativity, the principle that no influence can travel faster than light. He wrote to Max Born in 1947, "I cannot seriously believe in the quantum theory because it cannot be reconciled with the idea that physics should represent a reality in time and space, free from spooky actions at a distance." What is often missed in popular retellings of this debate is how reasonable Einstein's position seemed at the time, and to some extent still seems. We experience a world of definite objects with definite properties. The chair you are sitting in does not exist in a superposition of being in the living room and the kitchen. It is here. It has always been here. The moon exists, whether or not anyone looks at it. Einstein once asked Abraham Pais, "Do you really believe the moon is not there when nobody looks?" It was a rhetorical question, but it cuts to the heart of the matter. If quantum mechanics is complete, and particles truly do not have properties until measured, then at what scale does definite reality begin? Somewhere between the photon and the moon, things become real. Quantum mechanics, in its standard formulation, has nothing to say about where that line falls. This bothered Einstein. It should bother you. Bohr's response came within 6 weeks, also in Physical Review, with the exact same title. Can quantum mechanical description of physical reality be considered complete? His answer was yes, but his argument was notoriously difficult to follow. Bohr essentially rejected EPR's criterion of reality. He argued that you cannot talk about the properties of particle 2 independently of the experimental arrangement used to measure particle 1. The two particles, having interacted, form a single quantum system, and the experimental context determines what questions can meaningfully be asked. This is not about physical disturbance traveling between the particles. It is about the wholeness of the quantum phenomenon. A measurement context defines what is real, and different contexts define different realities. You cannot combine the results of incompatible measurements into a single picture any more than you can combine a photograph taken from the front with one taken from the side into a single flat image. The physics community largely sided with Bohr at the time, though many found his argument obscure. Einstein remained unconvinced until his death in 1955. For 3 decades, the EPR debate was considered a philosophical curiosity, interesting but empirically empty. Both sides agreed on what quantum mechanics predicted. They disagreed only about what it meant. Then, in 1964, an Irish physicist working at CERN did something remarkable. He turned a philosophical argument into a testable theorem. John Stuart Bell was 36 years old and working at the European Organization for Nuclear Research in Geneva when he published on the Einstein-Podolsky-Rosen paradox in the short-lived journal Physics. The paper was 6 pages long. It changed everything. What Bell proved was that Einstein's assumption that particles have definite properties before measurement and that influences cannot travel faster than light leads to measurable consequences, not philosophical consequences, empirical ones. He derived an inequality, a mathematical limit on the correlations between measurements on 2 separated particles that must be satisfied by any theory where particles carry pre-existing definite values determined by local hidden variables. Then he showed that quantum mechanics predicts violations of this inequality. This is worth pausing on. Before Bell, the debate between Einstein and Bohr was metaphysics. After Bell, it was physics. You could build an experiment, measure the correlations, and check whether they exceeded Bell's limit. If they did, Einstein was wrong. Not wrong about the math, wrong about reality. Local hidden variables. The idea that particles have definite properties all along and that distant measurements do not influence each other could not account for the results. The logic of Bell's theorem can be conveyed without equations, though doing it justice requires care. Imagine Alice and Bob are far apart. Each receives one particle from an entangled pair. Each chooses randomly among several possible measurements to perform. They record their results. Later, they compare notes. If the particles carried hidden instructions, a predetermined list of answers for every possible measurement, then the correlations between Alice and Bob's results are limited. There are only so many ways to distribute predetermined answers across multiple measurement settings. Bell's inequality captures that limit. It says, roughly, that if you calculate a certain combination of correlation measurements, the result cannot exceed a specific number, not for any strategy the particles might use, not for any hidden code they might carry, provided only that the code was determined locally and Alice's measurement choice does not affect Bob's outcome. Quantum mechanics predicts that entangled particles will produce correlations that exceed this limit, not by a tiny amount, by a substantial, experimentally detectable margin. For certain measurement angles, quantum correlations can violate Bell's inequality by a factor of the square root of 2, roughly 41%, above the classical limit. To make this concrete, consider polarization measurements on entangled photons. Alice and Bob each receive one photon from an entangled pair. Each sets their polarizer at some angle and measures whether their photon passes through or is blocked. If the photons carried hidden instructions, a predetermined polarization direction built in at the source, then when Alice and Bob compare their results across many rounds and many different angle settings, the rate at which their measurements correlate can never exceed a certain value. Bell's inequality captures that ceiling, but quantum mechanics predicts, an experiment confirms, that when Alice and Bob set their polarizers at specific relative angles, they get matching results more often than any hidden instruction set could produce. The excess is not subtle. It is robust, reproducible, and has now been confirmed in thousands of independent experiments across dozens of laboratories worldwide. The philosophical weight of this result is hard to overstate. It does not say that our current theory happens to predict something different from a hidden variable theory. It says that no possible local hidden variable theory, no theory where particles carry definite properties and influences travel no faster than light, can reproduce what nature actually does. This is not a limitation of quantum mechanics. It is a theorem about reality. The first serious experimental test came in 1982, when Alain Aspect, Philippe Grangier, and Gérard Roger at the University of Paris-Sud in Orsay performed a refined Bell test using entangled photons from calcium atoms. Their source produced pairs of photons in a cascade process, where a calcium atom excited by two lasers emits two photons in rapid succession, their polarizations perfectly correlated. Aspect's crucial innovation was using fast-switching acousto-optical devices to change the measurement settings while the photons were in flight. Previous experiments, including the pioneering 1972 test by John Clauser and Stuart Friedman at Berkeley, had used fixed polarizer settings. This left open the theoretical possibility that the particles, or the source, could somehow adjust to the settings in advance. By switching the measurements after the photons had left the source on a timescale shorter than the photon flight time, Aspect ensured that no subluminal signal could carry the measurement choice from one detector to the other. The switching happened every 10 nanoseconds. The photons flew for about 40 nanoseconds. The decision about how to measure each photon was made while it was already in flight, with no way for the information to reach the other side. The results violated Bell's inequality by 5 standard deviations. Einstein's local hidden variables could not account for what the photons were doing. Either the particles did not have definite properties before measurement, or influences were somehow propagating faster than light, or both. None of these options would have been acceptable to Einstein. All of them are acceptable to quantum mechanics. Aspect would share the 2022 Nobel Prize in Physics with John Clauser and Anton Zeilinger for these experiments. The Nobel Committee citation read simply for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. It took 40 years from Bell's theorem to Aspect's experiment, and another 40 years from Aspect's experiment to the Nobel Prize. The deep questions take time, but Aspect's experiment, as groundbreaking as it was, had loopholes. The detector efficiency was not high enough to rule out the possibility that only a biased subset of photon pairs was being detected, the so-called detection loophole, and the distance between the detectors was not large enough to completely eliminate the possibility of subluminal communication between them during the measurement process, the locality loophole. Closing these loopholes took 3 more decades of painstaking experimental work. The challenge was not just technical, it was conceptual. To close the locality loophole, you need the 2 detectors so far apart that light itself cannot travel between them during the measurement. To close the detection loophole, you need detectors efficient enough that essentially every entangled pair produces a registered click, eliminating the possibility that some biased subset is tricking you. Achieving both simultaneously in a single experiment was one of the great experimental challenges of 21st century physics. In 2015, 3 teams independently performed loophole-free Bell tests. Ronald Hansen's group at the Delft University of Technology in the Netherlands used a brilliantly elegant approach. They entangled nitrogen vacancy centers in diamond crystals, which are essentially single-trapped electrons held in a defect in a diamond lattice. These are not photons. They are matter, and they were separated by 1.3 kilometers, connected by fiber optic cables that ran underneath the university campus. The experiment used a technique called entanglement swapping. Each diamond emitted a photon entangled with its trapped electron. These two photons traveled to a detection station midway between the diamonds, where a joint measurement projected the distant electrons into an entangled state. Only when this heralding measurement succeeded, confirming that entanglement had been established, did the team perform the Bell test measurements on the electrons. This heralding step was the key to closing the detection loophole, because the electron spin measurements were essentially 100% efficient. Every entangled pair that passed the heralding step produced a valid data point. No fair sampling assumption was needed, and the 1.3 kilometer separation meant that light itself could not travel from one diamond to the other during the 4 microsecond measurement window. Both loopholes closed in a single experiment. The result violated Bell's inequality with a p-value of 0.039, equivalent to 2.4 standard deviations. This is modest by particle physics standards, but it was enough. The team ran 245 successful trials over a period of several weeks. Each trial required generating entanglement between 2 macroscopic diamonds over a kilometer apart, a feat that succeeds only about once every few minutes due to photon losses in the fiber. The patience required is hard to fathom. Simultaneously, a team at the University of Vienna, led by Anton Zeilinger, and a team at the National Institute of Standards and Technology in Boulder, Colorado, performed photon-based Bell tests with both loopholes closed. The Vienna group used entangled photons distributed over a 60-meter free space link and achieved a violation of over 11 standard deviations. The NIST team used an innovative detection scheme with superconducting nanowire photon detectors, operating at near unity efficiency, and exceeded 7 standard deviations. In 2018, the Big Bell Test Collaboration, organized by the Institute of Photonic Sciences in Barcelona, went further still. Over 100,000 volunteer participants from around the world generated random measurement settings by playing an online video game. Their keystrokes determined the polarizer angles in 13 simultaneous Bell test experiments across 12 laboratories on 5 continents. The goal was to address the freedom of choice loophole, the concern that perhaps the random number generators used to set the measurements were not truly random, but correlated with the hidden variables in some deterministic way by using human free will, or at least human unpredictability, as the randomness source. The collaboration made the superdeterminism loophole as uncomfortable as possible. Every experiment violated Bell's inequality. The results were published in Nature. The verdict was unanimous and unambiguous. Nature violates Bell's inequality. Local hidden variables are ruled out as an explanation of quantum correlations. Einstein's dream of a deeper, locally realistic theory underlying quantum mechanics is, at least in its simplest form, dead. But notice what Bell's theorem does not say. It does not tell you which of the 3 assumptions is wrong. It says that local realism as a package is incompatible with quantum mechanics. Local realism means two things together. Realism, that particles have definite properties, whether you measure them or not, and locality, that a measurement on one particle cannot instantaneously influence another distant particle. Bell says you cannot have both. You must give up at least one. Standard quantum mechanics gives up realism. Particles do not have definite properties until measured. This is what Bohr argued all along. Many worlds gives up a certain notion of definiteness. Everything happens, so there are no unmade choices to worry about. Bohmian mechanics, developed by David Bohm in 1952, takes the most iconoclastic approach. It keeps realism completely. In Bohm's theory, particles always have definite positions and follow definite trajectories. There is no indeterminacy, no wave function collapse. The price is explicit non-locality. Bohm's theory adds a pilot wave, also called the guiding equation, that steers particles along their paths. This pilot wave is a real physical field that permeates all of space and responds instantaneously to changes anywhere in the universe. When you measure one entangled particle, the pilot wave updates globally and instantly, changing the trajectory of the distant partner. This is not a signal. It cannot be used to communicate, but it is a real, faster-than-light influence on the particle's motion. Bohm traded the weirdness of indeterminacy for the weirdness of non-locality, and many physicists consider it a fair swap. The theory makes exactly the same predictions as standard quantum mechanics for every experiment ever proposed, including the quantum eraser. It just tells a very different story about what is happening behind the scenes. And the retro-causalists, like Hugh Price, try to keep both locality and realism by allowing influences to travel backward in time, which loosens the statistical independence assumption that Bell's theorem requires. Each of these responses to Bell has active defenders. None has been definitively ruled in or out by experiment. The question that Bell opened in 1964, which assumption about reality must we surrender, remains one of the deepest open questions in all of science. And this is the context in which entanglement moved from philosophical embarrassment to the central concept in quantum physics. Einstein called it spooky action at a distance and meant it as an insult. He believed it proved that quantum mechanics was incomplete. Bell showed it was real. Aspects showed it was measurable. The 2015 experiments showed it was inescapable. Entanglement is not a mysterious force connecting distant particles. It is a correlation, but a correlation of a kind that has no classical equivalent. When two photons are entangled, measuring one does not send a signal to the other. It does not cause the other to change, but it does reveal information about what a measurement on the other will find. And the strength of this correlation exceeds anything the pre-established agreements between the particles could produce. This is the content of Bell's theorem, and it is the content of the quantum eraser. In the Kim experiment, the signal photon and the idler photon are entangled from the moment of their creation at the BBO crystal. This entanglement is what encodes the witch path information in the idler. It is what suppresses interference in the signal, and it is what allows the erasure to work, because the witch path information is stored in a single quantum system, the idler, rather than being irreversibly amplified into the thermal environment the way it would be if you put a physical detector at the slits. The entire experiment is a precisely controlled demonstration of what EPR identified in 1935, what Bell formalized in 1964, and what Aspect confirmed in 1982. The quantum eraser is EPR made visible, complementarity made operational, and Bell non-locality made tangible. Understanding this chain, from Einstein's objection to Bohr's response to Bell's theorem, to Aspect's experiment, to Scully's proposal to Kim's realization, is essential. Without it, the quantum eraser looks like a magic trick. With it, it looks like the culmination of the single most important argument in the history of physics. There is a coda to this story that Einstein, who died in 1955, never lived to see. The spooky action he despised became the foundation of an entirely new technology. In 1993, Charles Bennett at IBM, Gilles Brassard at the University of Montreal, and 4 other physicists published a paper showing that entanglement could be used to teleport quantum information from one location to another. Not science fiction teleportation. The physical particle stays where it is, but its quantum state, the complete specification of every property it possesses, is transferred to a distant particle, using entanglement as the channel and a classical communication link as the trigger. The original state is destroyed in the process, consistent with the no-cloning theorem, which forbids making perfect copies of quantum information. Bennett and Brassard called it quantum teleportation, and it has since been demonstrated over distances exceeding 1,400 kilometers using the Chinese satellite Mixus. Notice the structure. You need entanglement between 2 particles. You need a measurement on one side. And you need a classical communication channel to tell the other side what to do with their particle. Without the classical channel, the distant particle is useless. The correlations are there, but inaccessible. Sound familiar? It should. Quantum teleportation has exactly the same logical structure as the quantum eraser. Entangled correlations that are invisible without classical information exchange. The no communication theorem in action. The quantum eraser is, in a very real sense, quantum teleportation's conceptual cousin. Both demonstrate that entanglement creates correlations that transcend distance, but that can never substitute for classical communication. This realization that entanglement is not a bug but a resource triggered the quantum information revolution. Quantum key distribution, which uses entangled photons to create provably unbreakable encryption, has been deployed on fiber networks in China, Europe, and the United States. Quantum computing, which exploits superposition and entanglement to perform certain calculations exponentially faster than any classical computer, has grown from a theoretical curiosity into a global industry. Google, IBM, Microsoft, and dozens of startups are racing to build machines that harness exactly the correlations the quantum eraser demonstrates. Einstein thought entanglement was an argument against quantum mechanics. It turned out to be quantum mechanics' greatest technological gift. But Scully's 1991 paper contains something else, something that would take 8 more years to test in a laboratory. If entanglement with a detector is what kills interference, Scully asked, then what happens if you erase that entanglement? What if you destroy the witch path information after it has been created? Could you bring the interference back? The answer, he showed theoretically, was yes. But the way it works is not what anyone expected. Before we get to the eraser experiment itself, we need to talk about John Archibald Wheeler, because what he proposed in 1978 is the conceptual foundation that makes the quantum eraser so disturbing. And Wheeler was not some fringe thinker. He was Richard Feynman's doctoral advisor at Princeton. He coined the term black hole. He coined the term wormhole. He worked on the Manhattan Project. When Wheeler proposed something, the physics community paid attention, even when what he proposed sounded insane. Wheeler's delayed choice thought experiment starts with a standard interferometer. A photon enters and hits a half-silvered mirror, a beam splitter, which gives it a 50-50 chance of being reflected or transmitted. The photon is now in a superposition of two paths. These paths are redirected by mirrors to a crossing point. Now the experimenter has two options. Option 1, the open configuration. Place detectors past the crossing point, one on each path. Each detector fires 50% of the time. The photon went one way or the other. Particle behavior. Option 2, the closed configuration. Insert a second beam splitter at the crossing point. Now the two paths recombine and interference occurs. One detector fires every time. The other detector never fires because constructive interference sends all the probability amplitude to one output and destructive interference cancels the other. Wave behavior. Here is the twist. Wheeler proposed that the experimenter wait until the photon has already entered the interferometer, already passed the first beam splitter, and is already well on its way down one path or both paths, and then, at the very last moment, decide whether to insert the second beam splitter or not. The decision about whether to observe wave behavior or particle behavior is made after the photon has already, in some sense, committed to its route. Wheeler wrote about this in his 1983 essay, Law Without Law. Thus one decides whether the photon shall have come by one route or by both routes after it has already done its travel. But Wheeler did not stop there. He imagined scaling this up to cosmic proportions. There is a real astronomical object called the twin quasar, catalogued as Q0957 plus 561. It is a single quasar whose light is split into two images by the gravitational field of an intervening galaxy, a phenomenon called gravitational lensing. The light left the quasar billions of years ago. It traveled along two paths around the lensing galaxy, paths separated by roughly 50,000 light years, and it arrives at Earth as two images. Wheeler proposed the following. Place a detector on Earth that can either determine which path each photon took, the left image or the right image, or combine the two paths to create interference. Make the choice now. The photon left the quasar billions of years ago. It passed the galaxy millions of years ago. The decision about whether it traveled one path or both paths is made after the light has been traveling for longer than the Earth has existed. As Wheeler put it, the photon has already passed that galaxy billions of years before we made our decision. This is the sense in which, in a loose way of speaking, we decide what the photon shall have done after it has already done it. Now, Wheeler was very careful about what he concluded from this. He was not arguing for backwards time travel. He explicitly stated that consciousness has nothing whatsoever to do with the quantum process. What he was arguing was something more radical in a different direction. He was arguing that the past does not have a definite existence until it is recorded in the present. His exact words: "It is wrong to think of that past as already existing in all detail. The past is theory. The past has no existence except as it is recorded in the present." Wheeler drew a picture he called the Great Smoky Dragon. It has a sharp tail, the emission event, and a sharp mouth, the detection event. But the entire body of the dragon between source and detector is obscured by impenetrable smoke. "What the dragon does or looks like in between," Wheeler said, "we have no right to speak. We know where the photon started. We know where it ended up. Everything in between is not merely unknown. It is, in a precise quantum mechanical sense, undefined." In 2007, Vincent Jacques and colleagues, including Alain of Beltès fame, confirmed Wheeler's predictions experimentally using true single photons from a nitrogen vacancy center in a diamond crystal. Their interferometer had a 48-meter path length. A quantum random number generator made the choice between open and closed configurations, and that choice was space-like separated from the photon's entry into the device, meaning no signal traveling at or below the speed of light could have communicated the choice to the photon before it entered. The closed configuration showed 94% interference visibility. The open configuration showed path determination with errors below 1%. Every prediction of quantum mechanics was confirmed. In 2015, Andrew Manning and colleagues at the Australian National University extended this to massive particles. Using ultra-cold metastable helium atoms and Bragg pulse beam splitters triggered by a quantum random number generator, they showed that even atoms, which have mass, interact with electric fields and are, in every sense, real physical objects, show the same delayed choice behavior as photons. As PhD student Roman Kakimov put it, to have done the experiment with atoms, which are complicated things that have mass and interact with electric fields and so on, adds to the weirdness. So by the late 1990s, the conceptual pieces were in place. Scully had shown theoretically that which path information could be erased to restore interference. Wheeler had shown that the choice between wave and particle behavior could be delayed until after the photon had already traveled its path. The next step was inevitable. What if you combined both ideas? What if you created which path information, let the photon be detected, and then, after the detection was already recorded, decided whether to erase the information or keep it? That is exactly what Yoonho Kim, R.U., S.P. Kulik, Yanhua Shi, and Marlon Scully did at the University of Maryland, Baltimore County. And to understand why their results are so unsettling, you need to understand every piece of their apparatus, not the hand-wavy version, the actual experiment. The paper was published on January 3rd, 2000, in Physical Review Letters, Volume 84, pages 1 through 5. A preprint had appeared on the Arkhangshef on March 13th, 1999. The title was simply A Delayed Choice, Quantum Eraser. It is one of the most discussed, most misunderstood, and most frequently misrepresented experiments in the history of physics. It starts with a laser, specifically a 351.1 nanometer argon ion laser, which produces ultraviolet light invisible to the human eye. This laser beam is aimed at a barrier with 2 slits, and then the light that passes through those slits hits a crystal. not just any crystal, a piece of beta barium borate, chemical formula BAB2O4, chosen for its remarkable non-linear optical properties. This crystal does something extraordinary. Through a process called spontaneous parametric down conversion, or SPDC, it converts a single ultraviolet photon into a pair of lower energy photons. Energy conservation requires that the two new photons have a combined energy equal to the original. Momentum conservation requires their combined momentum to match as well. The result is two photons, each with a wavelength of 702.2 nanometers, just past the red edge of visible light in the near infrared. These two photons are entangled. Their properties are quantum mechanically correlated in ways that have no classical explanation. The crystal is configured for what is called type 2 phase matching, which means the two photons in each pair have perpendicular polarizations, one ordinary and one extraordinary. This polarization difference is what allows them to be physically separated. A device called a Glan-Thomson prism, made of calcite crystal, splits the two photons into different spatial paths based on their polarization. Now here is the critical geometry. The laser passes through a double slit before hitting the BBO crystal, illuminating two distinct regions labeled A and B. These regions are separated by about 0.7 millimeters, with each region about 0.3 millimeters wide. When a photon pair is created, it is created at either region A or region B. This means the signal photon, the one heading upward toward the main detector, effectively came through one slit or the other, and its entangled partner, the idler photon heading downward, carries information about which region, which slit, produced the pair. The signal photon travels upward through a lens that performs a Fourier transform, mapping the diffraction pattern onto the focal plane, and hits detector D0. This detector is mounted on a stepper motor that scans it slowly along the horizontal axis, recording how many photons arrive at each position. D0 is the screen in our double-slit experiment. If interference is happening, D0 will show fringes, alternating peaks and valleys as it scans across. If interference is not happening, D0 will show a single featureless hump. Now for the idler photon. This is where the experiment gets intricate, and every piece matters. After leaving the Glan-Thomson prism, the idler photon hits a prism labeled PS that increases the spatial separation between idlers that came from region A and idlers that came from region B. The two paths then encounter two 50-50 beam splitters, BS sub A and BS sub B. If the idler came from region A, it hits beam splitter A. There is a 50% chance it reflects off this beam splitter and goes directly to detector D4. If that happens, we know the idler came from region A, which means the signal photon came through slit A. Which path information is preserved, but there is also a 50% chance the idler passes through beam splitter A and continues onward to a mirror, M sub A, which redirects it toward a final beam splitter labeled simply BS. The same thing happens on the other side. If the idler came from region B, it hits beam splitter B. 50% chance it reflects directly to detector D3. Which path preserved? Slit B this time. 50% chance it passes through to mirror M sub B and onward to beam splitter BS. And beam splitter BS is the quantum eraser. At this final beam splitter, idler photons that pass through from the A side and idler photons that pass through from the B side are combined. A photon arriving at BS could have come from either region. There is no longer any way, even in principle, to determine which slit produced it. The which path information has been erased. This beam splitter has two output ports, leading to detector D1 and detector D2. So to summarize the 5 detectors, D0 catches the signal photon and records its position. D1 catches idler photons whose which path information was erased at beam splitter BS. So does D2, the other output port of the eraser. D3 catches idler photons that were reflected at beam splitter B, preserving which path information for slit B. D4 catches idler photons reflected at beam splitter A, preserving which path information for slit A. 5 detectors, 1 signal photon detector, and 4 idler photon detectors. 2 of the idler detectors erase which path information. 2 preserve it. For each entangled pair produced, the signal photon always goes to D0, and the idler photon ends up at one of the 4 idler detectors, chosen by the random chance of beam splitter reflections. And here is the fact that makes this a delayed choice experiment. The idler photon's path through the apparatus is approximately 2.5 meters longer than the signal photon's path. Light travels about 30 centimeters per nanosecond. That 2.5 meter difference means the signal photon arrives at D0 approximately 8 nanoseconds before the idler photon reaches any of its detectors. The detectors have a timing resolution of about 1 nanosecond, so this ordering is unambiguous. The signal photon is detected, recorded, done, finished, past tense, before the idler photon has even reached the beam splitter that will decide whether its which path information is erased or preserved. 8 billionths of a second. That is not a lot of time in human terms. But in the world of this experiment, it is an eternity. The signal photon's fate is sealed before the universe has decided what to do with its twin. Now for the results. And this is where almost every popular account of this experiment gets it wrong, because they leave out the single most important detail. All 5 detectors are connected to coincidence circuits. These are electronic systems that register a count only when D0 and 1 of the other detectors fire within a narrow time window, adjusted for the known 8 nanosecond delay. So the experiment does not just record where signal photons land. It records where signal photons land and which idler detector their partner hit. This produces 4 separate datasets gathered simultaneously as D0 scans along its axis. Dataset 1. Signal photons at D0 whose idler partners hit D1, the eraser detector. When you plot the coincidence rate R01 against the position of D0, you get a beautiful, clean, unmistakable Young's double-slit interference pattern. Bright fringes and dark fringes, exactly what you would expect from a wave passing through 2 slits. Dataset 2, signal photons at D0 whose idler partners hit D2, the other eraser detector. Also an interference pattern, but shifted by half a fringe width relative to dataset 1. Where dataset 1 has a peak, dataset 2 has a trough. Where dataset 1 has a trough, dataset 2 has a peak. They are complementary, mirror images of each other. This phase shift arises from the physics of the beam splitter. Reflection and transmission at a 50-50 beam splitter introduce a 90-degree phase difference, and the 2 output ports of BS therefore produce fringes that are offset by exactly pi. Dataset 3. Signal photons at D0 whose idler partners hit D3, the Which path detector for slit B. No interference whatsoever, just a single broad hump. A single slit diffraction envelope. Because the Which path information was preserved, there is only one quantum amplitude contributing to the pattern, and you need two amplitudes to get interference. There is nothing to interfere with. Dataset 4. Signal photons at D0, whose idler partners hit D4, the Which path detector for slit A. Same thing. No interference. A single broad hump, shifted slightly from dataset 3 because the photon came from the other slit. So far, this seems to confirm the spookiest interpretation. Signal photons whose partners were later erased show interference. Signal photons whose partners were later detected with path information intact show no interference. And the later here is real. The signal photons hit D08 nanoseconds before any of this was decided, but here is the detail that changes everything. The fact that the viral videos and the breathless articles almost always leave out. Look at the total pattern at D0. Not sorted by coincidence, not divided into subsets, just the raw, unsorted data of every signal photon that hit D0, regardless of what happened to its partner. There is no interference pattern. None. It is a featureless blob. This is not a minor detail. This is the entire point. The mathematics explains why. Dataset 1 has fringes that go as cosine squared. Dataset 2 has fringes that go as sine squared. Add them together. Cosine squared plus sine squared equals 1. The two complementary interference patterns, shifted by exactly half a fringe, cancel each other perfectly. Add datasets 3 and 4, which are already featureless humps, and the total is a smooth, structureless distribution. No observer watching D0 in real time without access to the coincidence data from the idler detectors could ever determine whether which path information was being erased or preserved. The interference is invisible in the total signal. It exists only when you sort the data into subsets, and that sorting requires classical information from the idler detectors, information that can only travel at or below the speed of light. Think about what this means. If the future were actually reaching back to change the past, you would expect the total pattern at D0 to change when you switch the idler detectors on or off. It does not change, not even slightly. The signal photon distribution at D0 is identical regardless of what is happening downstream. The interference fringes were always there, hidden inside the total distribution, encoded in the correlations between entangled pairs. They are not created by the eraser. They are revealed by sorting. Sean Carroll, the Caltech and Johns Hopkins physicist and author, explains this with what I think is the clearest analogy available. Imagine you run a double-slit experiment, and the result on your screen is a featureless blob. Now someone comes along and says, I can sort your data into two groups, and each group will show interference fringes, but the fringes will be in complementary positions. That is not the future changing the past. That is post-selection. You are choosing which subset of your data to look at, and each subset has structure that the total does not. Sabine Hossenfelder, the German physicist and science communicator, puts it more bluntly. I could throw coins on the floor and then later decide to disregard some of those and create any kind of pattern. Clearly, this does not rewrite the past. Craig Gidney, a researcher at Google's quantum computing lab, wrote an influential analysis in 2016 called Erasure is Post-Selection. in which he identifies the exact point where the popular understanding goes wrong. People think that the quantum eraser works like a circuit, where an operation on one qubit affects the state of another, he writes. But actually, the other qubit is always unaffected. The key insight is that actual eraser experiments work by conditioning, which is post-selection, not by measurement affecting a distant particle. If Alice has one photon and Bob has the other, Bob has to tell Alice which runs to throw out before the pattern appears, and that telling requires a classical communication channel. No classical information, no pattern. This is guaranteed by a mathematical result called the no communication theorem, proved independently by several physicists in the late 1970s and early 1980s. It states that given a bipartite quantum system, any operation one party performs on their subsystem leaves the other party's reduced density matrix completely unchanged. There is no measurement Bob can perform on his photon that will produce any detectable change in Alice's photon. Period. The correlations are there, but they are invisible without comparing notes, and comparing notes requires classical communication. The quantum eraser does not rewrite the past. It demonstrates that the past contains hidden structure that can only be extracted through correlations between entangled particles, correlations that require classical information exchange to access. But if the experiment does not prove backwards time travel, and it does not prove that consciousness creates reality, and it cannot be used to send messages through time, then why do physicists still find it fascinating? Why is it still discussed in serious journals a quarter century after it was performed? Because what the experiment actually demonstrates, once you strip away the misinterpretations, is deeply and genuinely strange. And the strangeness is not about time, it is about the nature of reality itself. Let us start with the thing that even physicists who have debunked every retrocausal claim about this experiment still find remarkable. When you look at the raw data from D0, with no sorting, no coincidence counting, no information from the idler detectors, you see a smooth, featureless distribution. There is no interference pattern. There is no structure. It looks like exactly what you would get if you fired photons through two slits and measured which slit each one went through. It looks, in other words, like particle behavior, but hidden inside that featureless blob, encoded in the quantum correlations between each signal photon and its entangled idler partner, are not one, but two complete interference patterns. They are shifted by exactly half a fringe width, so they cancel when combined. And they can be extracted perfectly by sorting the D0 data according to information gathered billions of nanoseconds later at the idler detectors, or 8 nanoseconds later in the actual experiment. But the point is that the time does not matter. The patterns are always there. They are latent. They are a property of the entangled state from the moment of its creation. Sean Carroll captures this precisely. There was secretly interference hidden in what initially looked like a featureless smudge. The entangled state contains within it the correlations needed for every possible measurement result, wave-like, particle-like, or anything in between, regardless of which measurement is actually performed. The quantum state does not commit to one description or another. It holds all of them simultaneously, and the one you see depends entirely on how you choose to look. This is not like a coin that is either heads or tails, and you just do not know which. That would be classical ignorance. This is fundamentally different. The photon does not have a definite path that you simply fail to observe. Before the correlations are examined, the concept of which path does not apply, not because of any limitation in your instruments, because the universe has not yet defined an answer to that question. The answer comes into existence through the act of measurement, and different measurements bring different answers into existence, all from the same underlying state. Think about what that means for the concept of history. We think of the past as fixed. Things happened. The photon went through slit A or slit B. Its position at each moment along its trajectory was some definite fact. Wheeler's delayed choice experiment already challenged this assumption. The quantum eraser takes it further. The signal photon hits D0 at a specific location. That is a fact. It is recorded. It is in the past. But was that photon part of an interference pattern or not? That question does not have a definite answer. It depends on how the idler photon is measured, and that measurement can happen later, or in principle, could happen much later. The signal photon's participation in an interference pattern is not a property of the signal photon alone. It is a property of the correlation between the signal photon and the idler photon, and that correlation can be sliced in different ways. This is not the future, changing the past. The past, at D0, is always the same featureless blob. Nothing about D0 ever changes, but the meaning of that past, the pattern that can be extracted from it, the story you can tell about it, depends on measurements that have not yet occurred. The past is definite in its raw facts, but indefinite in its interpretable structure. Wheeler said it best. The past has no existence except as it is recorded in the present, and the quantum eraser shows exactly how that principle operates in practice. The second genuinely strange result confirms something Scully demonstrated theoretically in 1991, but that the eraser makes vivid. Interference is destroyed not by physical disturbance, but by information, not by jolting the photon, not by bumping it or kicking it or scattering anything off it, just by the mere existence, anywhere in the universe, of a physical record that could in principle reveal which path was taken. This is a profound shift from how we usually think about cause and effect. In classical physics, if you want to change the behavior of a particle, you have to interact with it, push it, hit it with another particle, transfer energy or momentum. There has to be a local physical mechanism. The quantum eraser demonstrates that none of that is necessary. The signal photon is not disturbed in any way by the idler photon's journey through the apparatus. No energy is exchanged between them after they leave the BBO crystal. No force is exerted. They do not communicate. And yet, whether the signal photon is part of an interference pattern depends entirely on what happens to the idler. As Maria Violaris wrote in Physics World in 2025, the most dramatic implication of the quantum eraser is explaining the role of observers in the double-slit experiment. The quantum eraser emphasizes that even a single entanglement between two qubits will cause decoherence, whether or not it is measured afterwards. No mysterious macroscopic observer is required. The mechanism is entanglement. When the signal photon is created at region A or region B of the BBO crystal, its twin idler photon carries a record of which region. That record does not need to be read. It does not need to be processed or perceived by any conscious entity. Its mere existence is sufficient to suppress interference in the signal photon. And when that record is destroyed, when the idler is routed through beam splitter BS and the two paths are recombined such that the origin information is permanently lost, the interference can be recovered from the correlations. Information, not interaction, is what governs wave-particle complementarity. And information, in quantum mechanics, is physical. It has physical consequences. Its existence or absence reshapes the statistical patterns of particles that may be arbitrarily far away, connected only by the invisible thread of entanglement. This idea that information is not abstract but physical has roots that go deeper than quantum mechanics. In 1961, Rolf Landauer at IBM proved that erasing a single bit of information in a computer necessarily generates a minimum amount of heat, a tiny but non-zero energy cost dictated by the second law of thermodynamics. Landauer's principle has been experimentally confirmed. Information is not just something we know about physical systems. It is itself a physical quantity, as real as energy or momentum, subject to conservation laws and thermodynamic constraints. The quantum eraser takes Landauer's insight and sharpens it to a razor's edge. The which path information stored in the idler photon is not a human concept imposed on the experiment. It is a physical fact about the state of the idler, a fact that has measurable consequences for the signal photon's behavior. Erasing that information is not just forgetting. It is a physical process, the recombination of two paths at beam splitter BS that destroys a physical record and, in doing so, changes what correlations can be extracted from the data. John Archibald Wheeler summarized this worldview with his famous phrase it from bit. Every particle, every field of force, even the space-time continuum itself, derives its function, its meaning, its very existence entirely from the answers to yes or no questions, binary choices, bits. The quantum eraser is perhaps the cleanest experimental demonstration of it from bit in all of physics. The interference fringes are not created by photons or waves or particles. They are created by the information structure of the entangled state. Change the information, and you change the pattern. Not the physical interaction, the information. The third genuine strangeness is the one that connects the quantum eraser to the deepest unsolved problem in physics. In 2013, Xiao Songma, Anton Zeilinger, and colleagues performed a version of the quantum eraser where the erasure choice was space-like, separated from the interference measurement. Space-like separated means that no signal traveling at or below the speed of light could connect the two events. They are causally disconnected. One cannot influence the other by any known physical mechanism. They did this at two scales. First, using a 55-meter fiber optic link in Vienna. Then, using a 144-kilometer free space link between the islands of La Palma and Tenerife in the Canary Islands. Entangled photons were generated on one island. Measurements were performed on both. The erasure choice was made by a quantum random number generator on the distant island. Interference visibility reached 0.951, nearly perfect, and the results matched quantum mechanical predictions exactly. Their conclusion, published in the Proceedings of the National Academy of Sciences, was unambiguous. No naive, realistic picture is compatible with our results. because whether a quantum could be seen as showing particle or wave-like behavior would depend on a causally disconnected choice. It is therefore suggestive to abandon such pictures altogether. What they are saying, in careful academic language, is that the quantum correlations revealed by the eraser are not the result of any hidden signal passing between the photons. They are not caused by the erasure choice somehow reaching across space to influence the distant measurement. The correlations are built into the entangled state from the moment of its creation, and they are stronger than anything a classical, locally realistic model can produce. This is Bell non-locality, the same phenomenon confirmed by loophole-free Bell tests in 2015 by teams in Delft, Vienna, and at NIST. The quantum world permits correlations between distant events that exceed what any local mechanism can explain. And yet those correlations can never be used to send a signal. The quantum eraser is, at its core, just EPR Bell correlations, viewed through a Witch path and interference lens. But it makes the non-locality tangible in a way that abstract Bell inequality violations sometimes do not. You can point to the interference fringes and the featureless humps and say, look, the same signal photons detected at the same time in the same way produce different patterns depending on what happens to their partners somewhere else. No signal was sent, no force was exchanged, and yet the correlations are there. That is the real mystery. Not time travel, not consciousness, not the future rewriting the past. The real mystery is that quantum mechanics allows correlations between space-like separated events that no classical theory can reproduce, while simultaneously forbidding anyone from using those correlations to communicate. The universe permits non-local correlations, but forbids non-local signaling. It is as if nature found the exact boundary between strangeness and paradox and camped on it. So, what do physicists actually think is going on? Not the pop science version, not the viral video version. What do the serious interpretations of quantum mechanics say about the quantum eraser? The Copenhagen interpretation, Bohr's original framework, handles the results through complementarity. Wave behavior and particle behavior are mutually exclusive. When Witch path information exists anywhere in the universe, interference is suppressed. When it is erased, interference can be recovered from the appropriate subset of data. Wheeler, working squarely in this tradition, emphasized that it is wrong to attribute a tangibility to the photon in all its travel from the point of entry to its last instant of flight. In Copenhagen, the photon does not have a trajectory between preparation and detection. It does not go through slit A or slit B or both. The question is meaningless outside the context of a specific measurement. The limitation of Copenhagen, and it is a real one, is that it never specifies exactly where the boundary falls between the quantum world, where superposition reigns, and the classical world, where definite outcomes occur. It posits what Heisenberg called the cut between quantum and classical, but leaves its location as a matter of pragmatic judgment rather than fundamental principle. The many worlds interpretation, championed by Sean Carroll and originally proposed by Hugh Everett in 1957, eliminates the mystery almost entirely at the cost of accepting a truly staggering ontology. In many worlds, there is no wave function collapse, ever. The universal wave function evolves unitarily and deterministically at all times. When a measurement occurs, the universe does not choose one outcome. All outcomes happen. The universe branches. For the quantum eraser, Carroll's analysis is explicit. When the signal photon becomes entangled with the idler at the BBO crystal, the two form a joint quantum state. The signal going through slit A is correlated with the idler going through path A. The signal going through slit B is correlated with the idler going through path B. These two components are now distinguishable, so they cannot interfere. Carroll's summary is that entanglement of any sort kills interference. But this decoherence is, in his words, kind of decohered. The which path information is stored in just one qubit, the idler photon, not irreversibly amplified into the thermal environment. Because the idler is a simple quantum system, its which path information can be erased by measuring it in a different basis. When the idler goes through beam splitter BS, the joint state is re-expressed in a new basis where each idler outcome is correlated with a signal photon that went through Bohr slits. Interference appears in each subset, but the two subsets have complementary fringes that cancel when added. Carroll concludes that nothing really went backwards in time. The branching of the wave function happened when the photon pair was created. The eraser measurement does not undo the branching. It merely sorts the branches in a way that reveals interference in certain subsets. True decoherence, the irreversible kind that makes everyday objects behave classically, takes a tiny quantum entanglement and amplifies it into the environment. In that sense, he writes, the delayed choice quantum eraser is a useful thought experiment to contemplate the role of decoherence and the environment in measurement. Carlo Rovelli's relational quantum mechanics, proposed in 1996, takes a different approach entirely. For Rovelli, quantum states are not observer-independent properties of the world. A photon does not have a path or an interference pattern in itself. These properties exist only relative to specific systems that interact with the photon. Relative to the which path detector, the photon has a definite path. Relative to a system that erases this information, it does not. And there is no contradiction, because there is no absolute observer-independent state. Rovelli has written that the world of quantum mechanics is not a world of objects, but a world of events, a world of relations. For the quantum eraser, this means the signal photon's behavior at D0 is not an intrinsic fact about the photon. It is a fact about the relation between the photon and the system that analyzes its correlations. Cubism, developed by Christopher Fuchs and Rediger Schack, goes further still. In Cubism, quantum mechanics is a user's manual that any agent can pick up and use to help make wiser decisions in this world of inherent uncertainty. The wave function does not describe the physical world. It describes an agent's beliefs about what will happen when they perform a measurement. Collapse is not a physical process. It is Bayesian updating, the revision of beliefs in light of new data. There is no retrocausality in the quantum eraser because there is no objective quantum state that could be changed backward in time. The interference pattern emerging from the sorted data is simply the consequence of updating one's predictions based on new information, which is what correlation always looks like. The consistent histories approach, developed by Robert Griffiths, Murray Gell-Mann, and James Hartley, provides yet another resolution. In this framework, quantum mechanics assigns probabilities to entire sequences of events called histories, but only when those histories satisfy a mathematical consistency condition. Asking which slit did the photon go through and asking does the signal show interference belong to incompatible frameworks, and the theory forbids combining questions from incompatible frameworks in the same analysis. The apparent paradox of the quantum eraser arises from mixing these incompatible questions. Griffiths has stated flatly that superluminal influences cannot carry information or anything else for the simple reason that they do not exist. 5 interpretations, 5 different stories about what is happening inside the apparatus. And here is the remarkable thing. They all make exactly the same predictions for every experiment that has ever been performed or ever will be performed. The disagreement is not about the physics. It is about the metaphysics, about what the math means, about what is real. This is the measurement problem, and it has been open since 1927. The quantum eraser did not solve it, but it clarified it. It showed, with mechanical precision, exactly where our classical intuitions break down and exactly what kinds of stories we are and are not entitled to tell about quantum events. There is a small but serious minority of physicists who do take retrocausality seriously as a feature of fundamental physics. It is worth being precise about what they claim and then what they do not. Hugh Price, the philosopher of physics at Cambridge, is the most articulate defender of the idea that physics should be time-symmetric at the fundamental level. His argument, spelled out in his 1996 book, Time's Arrow and Archimedes' Point, is that if the laws of physics are symmetric under time reversal, which they mostly are, then our insistence on forward-only causation is a prejudice, not a principle. The paradoxes of quantum mechanics, Price argues, are just the price we pay for being unwilling to contemplate the possibility that the future might be as significant as the past in determining the present. In 2017, Price and physicist Matthew Leifer proved a striking theorem. If you assume both that the laws of physics are time-symmetric and that the quantum state is a real physical thing rather than just a bookkeeping device, then retrocausality is a logical necessity. This is not a loose philosophical argument. It is a formal result, and it has a remarkable consequence. Retrocausality, if true, would provide an escape from Bell's theorem, because Bell's proof assumes the measurement settings are independent of hidden variables. If future measurement settings can influence past hidden variables, local hidden variable theories become possible again. This is why some serious physicists are interested, not because of YouTube videos about the quantum eraser, but because retrocausality could restore locality to fundamental physics. Yakir Aharonov, the Israeli-American physicist, famous for the Aharonov-Bohm effect, developed the two-state vector formalism with Peter Bergman and Joel Lebowitz back in 1964. In this framework, a quantum system is described not just by a state evolving forward from its preparation, but also by a state evolving backward from its future measurement. The combination of these two vectors gives a more complete description of the system at intermediate times. This led to the theory of weak values, published in 1988 with David Albert and Lev Vadman, where measured values of observables can fall far outside the normal range. Weak values have been confirmed experimentally and have practical applications in precision measurement. Feynman has noted that the two-state vector formalism fits very well with Hugh Everett's many worlds interpretation. John Cramer at the University of Washington proposed the transactional interpretation of quantum mechanics in 1986. Inspired by the Wheeler-Feynman absorber theory from the 1940s, Cramer models quantum events as handshakes between a forward-propagating alpha wave emitted by the source and a backward-propagating confirmation wave emitted by the absorber. The transaction, the completed handshake, is atemporal. It does not happen at a moment in time. It simply is. Ruth Kastner has developed this further, though she has also been one of the sharpest critics of retrocausal claims about the quantum eraser specifically, arguing that the experiment neither erases nor delays in the way commonly claimed. But these remain minority positions. Lorenzo Catani, a physicist at the International Iberian Nanotechnology Laboratory, stated in a 2025 RR-Xiv paper titled The Enigma of Delayed Choice Quantum Eraser that, as far as I know, only a minority of researchers have interpreted the experiment as evidence for retrocausality. The mainstream consensus, to the extent that such a thing exists in quantum foundations, is that the experiment is fully explained by standard quantum mechanics without any appeal to backward causation. The debate continues. Price and Leifer's theorem is a real result with real implications. Aharonov's weak values have been experimentally confirmed. Cramer's transactional interpretation offers a coherent, if unconventional, picture of quantum processes. These are serious physicists making serious arguments. But the quantum eraser itself is not their strongest evidence. As Johannes Fankhauser showed in his 2019 paper, Taming the Delayed Choice Quantum Eraser, the experiment resembles a Bell-type scenario in which the paradox's resolution is rather trivial, and so there really is no mystery. The mystery, if there is one, lies deeper in the nature of entanglement itself and in the measurement problem that has resisted resolution for nearly a century. Let me tell you about the people who actually did this experiment, because their stories are worth knowing. Yoon-Ho Kim was a graduate student at UMBC when he performed the experiment. He earned his PhD in 2001 with a dissertation on two-photon quantum entanglement under the supervision of Yanhua Shi. Today, Kim is professor of physics at Pohang University of Science and Technology, known as POSTECH, in South Korea, where he leads the Quantum Optics and Quantum Information Laboratory. He received the Korea Science Award in Physics in 2021 and was elected a Fellow of Optica, formerly the Optical Society of America, in 2022. His citation reads, "For significant scientific contributions in quantum optics on fundamental studies and applications of weak quantum measurement toward quantum information technology." His current work spans quantum imaging, quantum communication, and single-photon trapping in atomic ensembles. Yanhua Shi, Kim's advisor, founded the Quantum Optics Laboratory at UMBC in 1989 and has spent his career exploring the consequences of photon entanglement. He is co-inventor of ghost imaging, demonstrated in 1995, a technique that uses entangled photon pairs to create an image of an object using photons that never interacted with that object. Think about that. You shine light on an object, but the camera is pointed somewhere else entirely. The camera detects photons that never touch the object, yet by correlating them with their entangled partners that did touch the object, you reconstruct the image. Ghost imaging is now used in applications ranging from remote sensing to imaging through turbulent atmospheres. Scher received the Willis-Lamb Medal in 2002 for his pioneering contributions and authored the textbook An Introduction to Quantum Optics, Photon and Biphoton Physics. And then there is Marlon Scully. If the quantum eraser has an intellectual father, it is Scully. Born in 1939 in Casper, Wyoming, he earned his PhD at Yale under Willis-Lamb in 1966 and currently holds positions at Texas A&M University, Princeton, and Baylor simultaneously. His 1982 paper with Kai Druhl in Physical Review A was the theoretical proposal that the quantum eraser could work. It took 17 years for the technology to catch up. Scully has published over 700 papers. His contributions include the Scully-Lamb quantum theory of the laser, the first demonstrations of lacing without inversion, ultra-slow light propagation in hot gases, and quantum coherence techniques for real-time anthrax detection. His awards include the American Physical Society's Schollow Prize and the Optical Society's Frederick Ives Medal, which is their highest honor. He is a member of the National Academy of Sciences, the American Academy of Arts and Sciences, and the Academia Europaea. He is also a longtime cattle rancher in Texas, which has earned him the nickname the Quantum Cowboy. He holds a patent for a time-release medicine bolus for cattle. This is a man who studies the foundations of reality during the week and manages livestock on the weekends. Aharonov and Zubari wrote of Scully's work in the journal Science in 2005 that the quantum eraser effect of Scully and Druhl dramatically underscores the difference between our classical conceptions of time and how quantum processes can unfold in time. That assessment stands today. Since Kim and his colleagues published their results in 2000, the quantum eraser has not sat quietly on a shelf collecting citations. It has spawned an entire lineage of experiments, each one pushing the boundaries of what entanglement can do, each one sharpening the question of what quantum mechanics is really telling us about the world. In 2012, Xiaosong Ma, Anton Zeilinger, and their team at the University of Vienna published a paper in Nature Physics that might be the most conceptually disturbing quantum experiment since the original eraser. They realized a thought experiment that the Israeli physicist Asher Peres had proposed in 2000, just months before his death. Peres had asked a characteristically provocative question. Can you entangle two particles that have never coexisted? Here is what Ma and Zeilinger did. They created two separate pairs of entangled photons at different times. Call them pair 1 and pair 2. From pair 1, they measured photon A and recorded the result. From pair 2, they measured photon D and recorded the result. Then they took photon B from pair 1 and photon C from pair 2, the two photons that had never been entangled with each other, and performed a special joint measurement on them called a Bell state measurement. This measurement entangled B and C with each other, which, through a process called entanglement swapping, retroactively entangled A and D, the two photons that had already been measured and recorded. Think about that. Photons A and D were never entangled. They were measured, and their results were logged. Finished, done, in the past. And then, afterward, a measurement on their respective partners created entanglement between them, retroactively. When the researchers went back and saw the A and D data, according to the Bell state measurement results, they found quantum correlations that violated a Bell inequality by 4.7 standard deviations. The correlations were real, they were non-classical, and they were created after the fact. The authors were careful in their language, but the implication was startling. If one viewed the quantum state as a real physical object, they wrote, one could get the paradoxical situation that future actions seem to have an influence on past and already irrevocably recorded events. The word seem is doing a lot of work in that sentence. Marr and Zeilinger were not endorsing retrocausality. They were pointing out that interpreting the quantum state as a real physical thing creates a puzzle that does not arise if you treat it as a tool for calculating probabilities. Perez himself, who proposed this thought experiment, titled his 2000 paper Delayed Choice for Entanglement Swapping, and he ended it with one of the most provocative lines in quantum foundations. Unperformed experiments have no results. He was making a point about the futility of assigning definite quantum states to particles before measurements are actually performed. The entanglement between photons A and D does not exist and then get retroactively created by Victor's measurement. Rather, the correlations between A and D were always latent in the combined quantum state of the four-photon system from the moment both pairs were generated. Victor's Bell state measurement does not reach back in time. It determines which correlations are revealed when the data is sorted. Same mechanism as the Kim eraser, same resolution, same genuine strangeness lurking beneath that resolution. The experiment has the same resolution as the Kim eraser. The correlations are only visible when you sort the data according to the Bell state measurement results. The unsorted data shows no non-classical correlations at all. Post-selection, not retrocausation, but the fact that the sorting operation can retroactively reveal Bell-violating correlations between particles that were never entangled is, I think, genuinely mind-bending. Even if the mechanism is understood, the quantum eraser concept has since been extended in directions the original experimenters could not have anticipated. In 2014, a team led by Peng at Hefei demonstrated a delayed choice quantum eraser using thermal light rather than entangled photon pairs. This was significant because thermal light, the kind that comes from an ordinary hot source, was not thought to have the coherence properties needed for quantum interference. The experiment showed that even with messy, classical-seeming light, quantum correlations could be harnessed for erasure. In 2019, Wang and colleagues published a paper in Nature Photonics demonstrating something called quantum wave particle superposition in a delayed choice context. They created photons that existed in a genuine quantum superposition of being wave-like and particle-like simultaneously, not one or the other, depending on the measurement, but both at once. This goes beyond Bohr's complementarity, which assumed wave and particle aspects were mutually exclusive. The result does not contradict complementarity exactly, but it shows that the framework needs refinement. The Englert-Greenberger relation d squared plus v squared less than or equal to 1 allows for partial distinguishability and partial visibility, meaning the photon can exhibit both aspects to intermediate degrees at the same time. In 2020, researchers used ultra-cold rubidium atoms stored in a quantum memory to create a temporal version of Wheeler's delayed choice experiment. By storing a quantum state in an atomic ensemble and retrieving it later, they demonstrated that the delayed choice can be extended over macroscopic timescales, not just the nanoseconds of an optical experiment. The quantum memory held the state for microseconds, which does not sound long until you consider that in the quantum world, a microsecond is an eternity. Most quantum coherence experiments struggle to maintain superposition for more than a few hundred nanoseconds, and the concept continues to expand. In 2023, Kim and Ham demonstrated a quantum eraser using coherent photons in a Mach-Zehnder interferometer, publishing in Scientific Reports. In 2025, Yang and colleagues demonstrated quantum erasure using the orbital angular momentum of photons rather than their polarization, opening the door to higher dimensional quantum erasure. And Henke and colleagues have proposed using swift electrons in a transmission electron microscope to create a quantum eraser, which would demonstrate entanglement between free electrons and light, bridging the gap between quantum optics and electron microscopy. The double-slit experiment itself has been pushed to staggering scales. Interference has now been demonstrated with molecules containing up to 25,000 atomic mass units, roughly 2,000 atoms. These are not subatomic particles. They are genuine molecules, vastly more complex than individual photons or electrons, and they still show quantum interference when which path information is unavailable. The quantum world does not end at the atomic scale. It extends upward, and we still do not know where it stops, or if it stops at all. The molecules used in the largest interference experiments are synthetic organic compounds, purpose-built to be as massive as possible while still being launchable in a molecular beam. They are broader than some viruses. If you could line up about 10,000 of them end to end, they would span the width of a human hair. And each one of these molecules, containing thousands of protons, neutrons, and electrons bound together in an intricate chemical structure, passes through a grating and interferes with itself exactly as a single photon does. It goes through all the slits at once, or it goes through none of them, or the question does not apply. The math does not care how big the molecule is. It only cares whether the environment has recorded which path was taken. The current frontier is pushing this boundary toward biological molecules and eventually, perhaps, toward nanomechanical objects. Proposals exist for performing double-slit experiments with objects containing millions of atoms. Some theorists speculate about testing quantum superposition with objects visible to the naked eye, though the technical challenges are immense. Decoherence is the enemy. The larger the object, the more aggressively the environment entangles with it, recording which path information in the thermal bath of surrounding air molecules, photons, and gravitational fluctuations. Shielding a macroscopic object from environmental decoherence long enough to observe interference may require conditions not much better than the vacuum of deep space. But there is no known principle of physics that sets a hard boundary. No size limit, no mass limit, just a practical wall that gets harder and harder to scale. This is the deepest implication of the quantum eraser. The classical world, the world of definite positions and definite histories and objects that are here and not there is not a separate domain governed by separate laws. It is the quantum world, viewed through the lens of overwhelmingly redundant environmental measurement. The transition from quantum to classical is not a phase transition. It is a quantitative accumulation of entanglement with the environment, piling up so rapidly and so irreversibly that no conceivable eraser could undo it. Perhaps the most surreal offspring of the quantum eraser is the quantum Cheshire cat, an experiment that sounds like it was designed by Lewis Carroll and built by people who took the joke too seriously. In 2014, Tobias Denkmeyer and colleagues at the Vienna University of Technology used neutron interferometry to demonstrate what they called the separation of a particle from one of its properties. They sent neutrons through a silicon crystal interferometer and showed that the neutron itself traveled along one path, while its magnetic moment, its spin, traveled along the other. The cat was in one place. Its grin was somewhere else. To appreciate how weird this is, think about what a magnetic moment is. It is not a separate thing attached to the neutron. It is a fundamental property of the neutron, as intrinsic to it as its mass or its charge. Saying the neutron went one way while its spin went another is like saying you walked through a door but your height went through the window. It violates every intuition about what it means for a property to belong to an object. And yet, the weak measurement data showed exactly this separation. In 2020, Kim and colleagues demonstrated an exchange of grins between quantum Cheshire cats, where two photons appeared to swap their polarizations without ever classically meeting. Imagine two cats in separate rooms who somehow exchange smiles without either cat visiting the other room. That is, roughly, what happened. In 2023, a delayed choice version was performed, combining the Cheshire cat effect with the delayed choice paradigm, meaning the decision about whether to observe the separation was made after the neutrons had already passed through the interferometer. A 2024 study raised important questions about whether the particles truly separate from their properties or whether the effect depends on the measurement framework, echoing the same post-selection issues that arise in the quantum eraser. The debate is ongoing and sharpening. Some physicists argue the Cheshire cat is a genuine ontological surprise. Others argue it is an artifact of weak measurement statistics, as meaningful or meaningless as any post-selected subset. But the fact that we are seriously discussing experiments in which particles separate from their own physical properties tells you something about how far the quantum eraser's legacy extends. It forced physicists to think about which path information, measurement, and entanglement with a precision that has opened doors no one anticipated. In 2018, Rafael Chavez and colleagues identified a subtle loophole in Wheeler's original delayed choice argument. Using the mathematics of causal modeling, a framework that translates cause and effect relationships into rigorous graphical structures, they showed that a class of classical models could, in principle, reproduce the delayed choice results if certain assumptions about statistical independence were relaxed. Specifically, if the measurement settings were allowed to be correlated with hidden variables, a local realistic model could mimic quantum predictions. This is the same loophole that arises in Bell tests, sometimes called the freedom of choice or superdeterminism loophole. 3 experimental teams raced to close it. The approach was to use random number generators whose outputs were certified to be independent of the experimental conditions. The results, reported in Quantum magazine in July 2018, confirmed that a class of classical models that advocate realism cannot make sense of the results. The quantum predictions held, the loophole was closed, and the strangeness remained, now with one fewer escape hatch for the classically minded. Let me give you some numbers that anchor this abstraction to physical reality, because the quantum eraser can feel like pure philosophy until you realize that everything I have described happens to real photons in real laboratories measured by real instruments. The pump laser in the Kim experiment operates at 351.1 nanometers. That is ultraviolet, invisible to the human eye, with a wavelength about 5 times smaller than the diameter of a typical bacterium. The entangled photons it produces have a wavelength of 702.2 nanometers, near infrared, just past the red edge of what your eyes can detect. If you could see near infrared, these photons would appear as an impossibly deep red. For scale, a human hair is roughly 70,000 nanometers in diameter. The photon wavelength is about 100 times smaller than that, and the two regions on the BBO crystal where the entangled pairs are generated, regions A and B, are separated by 0.7 of a millimeter, with each region about 0.3 of a millimeter wide. The entire quantum drama plays out in a space you could cover with a grain of sand. The BBO crystal itself, beta barium borate, is a workhorse of quantum optics. It was first synthesized in the 1980s and rapidly became the standard for parametric down conversion experiments because of its wide transparency range, large nonlinear coefficient, and high damage threshold. But the down conversion process is spectacularly inefficient. Roughly 1 pump photon in a million produces an entangled pair. The other 999,999 pass through the crystal without doing anything interesting. Building up enough coincidence counts for a statistically meaningful result requires hours of patient data collection. The path length difference between signal and idler is about 2.5 meters. Light covers about 30 centimeters per nanosecond. So the idler photon, taking the longer route through the beam splitters and mirrors, arrives at its detector roughly 8 nanoseconds after its signal twin has already hit D0, 8 billionths of a second. In human terms, this is nothing, less than a blink, less than a heartbeat, but the detectors resolve timing to about 1 nanosecond, which means the ordering is unambiguous 8 times over. For the space-like separated version by Ma and Zeilinger, the distances are genuinely staggering. The 55-meter fiber link in Vienna is one thing, but the 144-kilometer free space link between La Palma and Tenerife stretches across open ocean. 144 kilometers is about the distance from London to Birmingham or from New York City to New Haven. Entangled photons were generated on one volcanic island, sent screaming through the atmosphere to another, and measured with sufficient precision to demonstrate interference visibility of 0.951. That is 95% of the maximum possible contrast. For comparison, the original Young experiment in 1801 used sunlight and 2 pinholes. The technology separating Young from Zeilinger spans 2 centuries and multiple revolutions in physics. But the fundamental question is the same one Thomas Young asked when he saw those bright and dark bands on his screen. What is light doing between the source and the detector? Young had an answer. It is a wave. The 20th century complicated that answer beyond recognition, and the quantum eraser suggests that maybe the question itself is the problem. Here is another way to feel the scale of what is happening. When the BBO crystal produces an entangled pair, the two photons are created within a time window of roughly a few femtoseconds. A femtosecond is a millionth of a billionth of a second. In 1 femtosecond, light travels about 300 nanometers, roughly the width of one of the illumination regions on the crystal. So the entangled pair is born in a space smaller than a bacterium and a time shorter than any chemical reaction. And from that speck of creation, the correlations extend outward, maintaining their quantum coherence across meters in the Kim experiment and across 144 kilometers in the Zeilinger version. It is as if two people born in the same hospital room on the same day maintained an unbreakable connection that determined the results of every coin flip they would ever make, no matter how far apart they traveled. Except it is not a hidden agreement. Bell's theorem proves that no pre-arranged strategy can reproduce the quantum correlations. The connection is real, irreducible, and unexplainable in any classical terms. The down conversion efficiency tells its own story about the patience required for this kind of science. A one entangled pair per million pump photons, and with coincidence rates of roughly 140 counts per scanning position at peak, the experimenters had to sit and wait while the apparatus quietly accumulated data, photon pair by photon pair, for hours. Each coincidence count represents a single entangled pair that happened to be created, happened to have its signal photon land at that particular scanner position, and happened to have its idler photon reach the right detector within the coincidence window. The vast majority of photons generated by the laser do nothing useful at all. The signal is buried in an ocean of irrelevant events, and extracting it requires meticulous calibration, precise alignment, and above all, time. So where does all of this leave us? Let me try to state as clearly as I can what the delayed choice quantum eraser actually demonstrates, stripped of every misinterpretation, every sensational headline, every pop science exaggeration. First, quantum systems do not have definite histories in the classical sense. A photon passing through a double slit does not go through slit A or slit B or both. It enters a quantum state that is a superposition of both possibilities, and that state does not resolve into a definite history until a measurement creates one. Different measurements create different histories from the same underlying state. Second, interference is not a property of individual particles observed in isolation. It is a property of correlations. When a photon is entangled with another system, the interference pattern is not gone. It is hidden in the joint correlations between the two systems. It can be extracted by appropriate measurements on the partner system, but only through post-selection, never by looking at the photon alone. Third, information, not physical disturbance, governs whether interference occurs. The mere existence of which path information anywhere in the universe, stored in any physical system, even if no one ever reads it, is sufficient to suppress interference. Destroying that information can restore interference to the correlated subsets of data. This is not a mechanical process. It is an informational one. And it tells us something deep about the relationship between information and physical reality. Fourth, quantum correlations between entangled particles are non-local. They are stronger than any classical mechanism can produce, and yet they cannot be used for signaling. This is guaranteed by the no communication theorem and is consistent with special relativity. The universe permits non-local correlations, but enforces local causality at the level of observable signals. How it manages this trick is one of the deepest open questions in physics. Fifth, none of this requires consciousness, observers, free will, or any other mystical ingredient. Decoherence, the entanglement of a quantum system with its environment, is a physical process that occurs continuously and automatically. It does not require a mind. It requires only an interaction that creates a correlation. A stray molecule bouncing off a photon near one slit is enough. The reason everyday objects do not show quantum interference is not that they are too big. It is that they interact with too many environmental particles. A baseball flying through the air is entangled with trillions of air molecules every second. Its which path information is recorded 1 trillion times over in the thermal bath of its environment. No quantum eraser could ever erase that much information. The classical world emerges from the quantum world not through some fundamental boundary, not through the Heisenberg cut that Copenhagen postulated, but through the sheer overwhelming redundancy of environmental decoherence. We live in a world that has been measured and measured and measured again by everything around it until no trace of quantum interference survives. And sixth, none of this is retrocausal. The past, as recorded in the raw data, never changes. What changes is how we sort that data. And sorting requires classical information exchange that respects the speed of light. The future does not rewrite the past. The past contains hidden structure that is revealed by future choices about how to analyze correlations. These 6 points are not controversial among physicists who study quantum foundations. They are the consensus. The controversies are about what lies beneath, about what the mathematics means, about whether the wave function is a real physical thing or a tool for calculating probabilities, about whether the universe branches every time a measurement occurs, or whether quantum states are relative to the observer, or whether the past and future conspire in ways we do not yet understand. Those are genuine open questions, debated by serious people making serious arguments. But the experiment itself, the experiment is clear, and yet there is something that even the most careful, most technically precise account of the quantum eraser cannot quite capture. Something that sits beneath the mathematics and the detector configurations and the coincidence counting circuits. Richard Feynman said, "Nobody understands quantum mechanics." And by that, he did not mean nobody can do the calculations. He meant that nobody has a satisfying picture of what reality is like at the fundamental level. The equations work. They predict with astonishing accuracy the outcome of every experiment ever performed, but the equations refuse to tell a coherent story about what is happening between measurements. They give you the beginning and the end, the sharp tail and the sharp mouth of Wheeler's dragon. They do not give you the body. The quantum eraser sharpens this refusal to an almost painful degree. It presents us with data that can be organized into complementary interference patterns or into featureless humps depending on how we slice it. The data itself does not change. Only the story we extract from it changes, and each story is internally consistent and experimentally confirmed. But the stories are mutually exclusive. Was the photon a wave? Look at the D1 coincidence data. Yes, clearly it was a wave. It went through both slits and produced interference. Was the photon a particle? Look at the D3 coincidence data. Yes, clearly it was a particle. It went through one slit and produced no interference. Was it both? Look at the total unsorted data. It was neither. It was a featureless average of all the stories, committing to none of them. The quantum eraser does not answer the question of what photons are. It does something more important. It shows that the question, as phrased in the language of classical objects, has no answer. The photon is not a wave. It is not a particle. It is not both. It is not neither. It is a quantum system, and quantum systems do not map onto any category that the human mind evolved to understand. We evolved to track medium-sized objects moving at moderate speeds in 3 dimensions. We did not evolve to intuit the behavior of probability amplitudes in Hilbert space. The strangeness of quantum mechanics is not a failure of physics. It is a failure of intuition, and the quantum eraser rubs our faces in that failure with uncommon clarity. But here is the thing I keep coming back to. The experiment works. The predictions are confirmed to extraordinary precision. The mathematics describes reality, even if we cannot visualize what the mathematics is describing. Whatever is happening between the source and the detector, between the tail and the mouth of Wheeler's dragon, it follows exact, precise, repeatable laws that we can write down and test. The universe is not capricious. It is not random. It obeys rules. We just cannot picture the rules in operation. And maybe that is enough. Maybe physics was never supposed to provide a picture. Maybe it was only ever supposed to provide a calculus, a set of procedures that allow you to predict outcomes with arbitrary precision. Newton gave us a picture of gravity as a force acting across space. Einstein replaced it with a picture of space-time curvature. But quantum mechanics resists pictures entirely. Every picture we try to impose, particles following trajectories, waves spreading through space, alternate universes branching off, information flowing backward in time, every single one captures some aspect of the truth while missing others. The quantum eraser demonstrates this with almost theatrical precision. Niels Bohr, who spent more time thinking about this problem than perhaps any human being who has ever lived, came to a conclusion that sounds defeatist, but might be the most honest position available. He said that physics is not about how the world is, but about what we can say about the world. Not what is real, but what can be meaningfully discussed. The quantum eraser lands squarely on Bohr's side of that argument. You can discuss the interference pattern in the D1 subset. You can discuss the featureless hump in the D3 subset. You can discuss the entangled state and the coincidence counting and the post-selection. What you cannot do without contradicting yourself or the data is describe what the photon was doing between the crystal and the detector. The body of the dragon is smoke, not because we lack better instruments, but because the smoke is the answer. In 1801, Thomas Young pointed sunlight through 2 holes and saw bright and dark bands on a wall. He concluded that light was a wave. That was the beginning of the story. In 1989, Akira Tonomura sent single electrons through a biprism one at a time and watched an interference pattern build up dot by dot. That was the middle of the story. In 1999, Yoon Ho Kim fired ultraviolet light into a barium borate crystal and watched entangled photons reveal interference patterns that only became visible when you asked the right questions about their partners, questions that could be asked after the fact from a distant location with no signal connecting the two. That was not the end of the story. There may not be an end. What connects Young's sunlit pinholes to Kim's entangled photons to Zeilinger's 144-kilometer ocean crossing is not just a technological progression. It is a deepening confrontation with the same unanswerable question. Every generation of experimenters has found a more sophisticated way to ask what light is doing between source and detector. And every generation has received the same reply. The universe will tell you where the photon starts. It will tell you where the photon ends. It will not tell you the story in between. And here is what I find most remarkable about the whole affair. This silence is not a limitation of our technology. Better detectors will not pierce it. Faster computers will not crack it. The silence is a feature of the theory itself. Quantum mechanics, the most precisely tested theory in the history of science, accurate to 14 decimal places in some calculations. That theory contains within its own formalism the declaration that certain questions have no answers. Not that we cannot find the answers, that the answers do not exist. The quantum eraser did not break reality. Reality was always like this. We just were not paying attention to the right experiment. Wheeler's great smoky dragon still hangs in the fog between source and detector. Its tail is sharp, its mouth is sharp, its body remains opaque. And the most honest thing physics can say about that body after 225 years of increasingly ingenious experiments is the same thing Wheeler said in 1983. We have no right to speak, but we can listen. And what the data is telling us, if we are patient enough and honest enough to hear it, is that the universe is under no obligation to make sense to creatures who evolved to dodge predators on the African savanna. It is under no obligation to provide a picture. It is only obligated to be consistent. And it is perfectly, maddeningly, beautifully consistent. Every single time we check,